think Highland. Just think Highland.
Welcome to our 10:30 press conference, which we've entitled Nuclear Weapons Testers Beware, New Technologies for Testing Treaty Verification. We have 4 speakers who will speak in this order. Patrick Grenard, Special Assistant to the Executive Secretary of the Comprehensive Nuclear Test Ban Treaty Preparatory Commission in Vienna, Austria. Gordon MacLeod, Chief Policy Planning and Operations Section, again at the Comprehensive Nuclear Test Ban Treaty Preparatory Commission in Vienna. Monica Custa, she's an Atmospheric Sciences Officer at the same institution. And Pierrick Mial, he's Acoustic Officer with the same institution.
Good morning. So my name is Patrick Grenard, and as a member of the Comprehensive Nuclear Test Ban Treaty Organization, so it's a pleasure to be here today at the AGU conference to present what we do and to engage and strengthen our ties with the scientific community. The Comprehensive Nuclear Test Ban Treaty, CTBT, bans all nuclear explosions anywhere by anyone. 17 years after it was opened for signatures, the treaty enjoys a near universal status, as 183 countries have already signed the treaty, therefore say no to nuclear testing, and 161 countries have already ratified the treaty, therefore saying never again to nuclear testing. As of today, 8 countries and remain to ratify for the treaty to enter into force. But in the meantime, so we keep building the verification system of the treaty and prepare for its entry into force. The test ban is verified by an unprecedented and very sophisticated verification system. It's composed of an international monitoring system that's a global network of stations all around the world, seismic stations, hydroacoustic, infrasound, radionuclide station transmitting data to an international data center in Vienna, Austria, where data are processed and analyzed by experts and before products are distributed to member states. The effectiveness of this international monitoring system to ensure that no nuclear explosion goes undetected has been proven already at 3 occasions. The system detected very well all the nuclear tests in North Korea. But there's more to that. The versatility of the system has also been proven in scientific and civil applications. A very good example is how the system reacted after the Great Tohoku earthquake in Japan in 2011. Our seismic stations registered the magnitude 9 seismic event, and its 10,000 aftershocks. Our infrasound stations detected the explosions at the Fukushima Daiichi nuclear power plant, and our radionuclide stations detected the emissions and from that nuclear power plant, whereas our atmospheric transport modeling system was able to predict the dispersion of nuclear materials all around the world. So our system is also contributing to tsunami warning, distributing data to tsunami warning centers, and the number of civil and scientific applications of the verification system is really blooming. So while the system is well established, and as I mentioned, demonstrated its effectiveness, so we keep improving this system. So performance is already much better than was initially envisaged when the treaty was opened for signature, but we keep improving the performance of the system And that's one of the reasons why we are here at this conference. It's really to exchange ideas and to continue to inject new developments into the system. And so you will see through the presentations of my colleagues that there is a number of interesting developments that illustrate really the improvements made to the performance of the system and the wide applications that we can have for civil and scientific purpose. So as a conclusion, this conference is essential for us because this improvement to the system, it's a scientific endeavor to mobilizing experts all around the world, and strengthening our ties with the community is essential. CTBTO is well represented at this conference. We had a very good union session where under Secretary of State and Rose Gottmuller, the Executive Secretary of the CTBTO, Lassina Zerbo, and Dr. Terry Wallace from Los Alamos, and Professor Raymond Jean Laws were invited speakers. So the session took place on Monday, but I invite you to attend another session that is organized on a Friday afternoon on CTBTO if you want to learn more about ourselves. So thank you very much.
Good morning. I'm going to actually now twist things a little bit because Patrick talked about the IMS and the IDC portion. I'm going to talk about the on-site inspection. My name is Gordon McLeod. I'm the Chief of Policy Planning and Operations, and I also am the Project Manager for the Integrated Field Exercise IFE 14. That we're going to be conducting next November, starting on the 3rd of November through December 9th in Jordan. It's going to be a full-scale exercise of the on-site inspection verification regime. And what's unique about that is, unlike the IMS and the IDC, which have provisional operation right now, actually really good provisional operation, we are still don't really come into being until there's actually the treaty in force. So we're in this planning mode where we're putting things together. So I'm going to talk a little bit about that just so you have an idea of what an on-site inspection is, and then try to demonstrate all the new technologies we've been bringing on board. And you'll see some of those technologies are what's being in the poster sessions and everything else being used. So these are the 4 verification regimes. Patrick just addressed the International Monitoring System, which has the seismic, hydroacoustic, infrasound, and radionuclide capabilities. We also have the International Data Center as part of that, which is doing the analysis of that, which I think Monica and Pierrick will address some of the things that go on with that. And then all of this is communicated through what we call the global communications infrastructure, which allows for the near real-time or real-time, depending on what you consider real-time, communications of all this data. And with that, I'm going to talk just about this light blue thing with the conduct of an on-site verification. And I apologize, this is, sometimes we do this for hours. I'm going to do this in minutes. So this is an on-site inspection. So you have data that comes from the International Monitoring System plus data from national technical meetings from the state parties. Those can be formulated into a request for an on-site inspection. That goes through a process with the Executive Council, which is referred to here as EC. And if there's approval of that, then you can actually do the inspection. The inspection can be up to 1,000 square kilometers. It's based on the data that comes in. This is currently represented in this graphic with the error ellipse, which is completely fictitious. And if you were to do a global search and figure out, this is a picture from Slovakia. But we were using this in an exercise, a build-up exercise earlier this year. Once you have the exercise area and all the inspectors, everything else, and roughly 100 tons of equipment shipped to the area of inspection within 6 days of the request, you start looking for facts and information on the ground. So we're not trying to make decisions on whether a nuclear test actually occurred or not, but just gathering facts using the techniques which I'll go through next. That then information then comes back, and the Executive Council, after the final report being submitted by the Director General of the CTBTO, puts that into the Executive Council for final decision. So these are the different techniques and technologies. So you have everything from MSIR infrared to basically still photography, environmental sampling, passive seismology, and then going through active seismic surveys, resonance seismometry, magnetic field mapping, gravitational field mapping, ground penetrating radar, electrical conductivity measurements, and ultimately you can do drilling. So we're trying to test this, as I mentioned, next year. We're going to be involving up to 80 inspectors. Only 40 can be on the ground at any one time, so we have rotation based on expertise, because you can't expect everybody to be able to do all those things I just mentioned. And so we have rotation. We'll end up having, if you do some additions and everything else, you'll come up to close to 200 to 300 people actually involved in this exercise when you start counting the evaluators and the observers from the state parties that want to see how this actually works. This is a comparison. We did this exercise initially in called IFE-08 in Kazakhstan. This was done, as I said, in 2008. We've now, if you notice the column in green, added an awful lot of technologies and techniques since then. And there's another slide that continues that as it goes through of what we can do now that we hadn't been able to do before. We just got done testing all these activities in an integrated manner in a series of build-up exercises. These took place, the last one took place from the end of May through beginning of June in Hungary. And that's where these pictures were taken. Oddly enough, we have a joke running about OSI weather because every time we seem to go out in the field, we have to bundle up like this, even in the middle of Europe in summer. So the key thing I wanted to convey in these last few minutes is that the IT will be able to field all those techniques I showed you and exercise those. They'll be doing it based on free play, so it's the IT that's actually making the decisions in negotiations with the people we have playing the inspected state party, which is the country being inspected, and utilizing what we have in the protocols of the treaty. What we have is operations manuals and SOPs for how we actively engage in the inspection. So my only thing is that from an exercise management standpoint is no matter what we plan for, they're going to do something different. Seems to be the first engagement rule. The other thing is that I'd like you to visit www.ctbto.org and then /IFE14, and there's a lot more newsletters, brochures, and information that you can gather from that. So thank you.
Good morning. My name is Monika Krista and I work as atmospheric scientist. And I'll say a few words about the role and then enhancement of the atmospheric transport modeling at CTBTO. So CTBTO, among other global networks, operates a global network of stations monitoring for presence of airborne radionuclides. Those airborne radionuclides can be in particulate form, but we also have equipment which is capable of detecting radioactive noble gas isotopes, namely xenon. And the importance of xenon stems from the fact that it is a chemically inert, non-depositing tracer, and therefore it's capable of is subject to long-range transport in the atmosphere and then capable of traveling from a potential release point to a detecting station. A detection at one of our stations is an accomplishment of a sophisticated measurement process, but it's also a beginning of a different process of finding the source of the detected radionuclides. To do so, we use an atmospheric transport model, which is a computer simulation, so a set of computer instructions which perform calculations in order to solve a mathematical model of propagation of tracers, and in this case radionuclides, throughout the atmosphere. So we release virtual particles, which each of them carries a certain amount of radioactivity and which are advected through the atmosphere, mainly according to wind velocity. Now, the meteorological information that we need in order to perform atmospheric transport modeling simulations comes on a grid. The same is valid for the atmospheric transport modeling itself and for the outputs. And then that means that we have one number per grid, let it be temperature, wind velocity, or the outputs of atmospheric transport modeling, but we're not able to distinguish between 2 points in the same grid. Therefore, as you may doubt, if the grid is finer, if we increase resolution, then we have better representation of the physical processes, and the same refers to those particles that we release within the model. So the computational power is a very important factor in increasing accuracy of our simulations. Now, the atmospheric transport modeling can be performed in two modes. The first one, the intuitive, is performed forward in time, and an example of this is shown in this animation at the top left-hand side slide, and the animation, where we know or suppose the location of the source, and we perform the simulation to the future to our stations where we should expect the detection. However, it is not frequent that we know the source, and more often we have to start from a detection of radionuclides, and in this case we perform atmospheric transport modeling simulations backward in time. An example of such a simulation is shown at the bottom right-hand side of the slide, where the regions indicated by the outputs of the model are those of air present over the surface of the Earth before it was sampled in our station, and that gives indication on the location of possible sources. As I said, the performance of atmospheric transport modeling computations and then their accuracy depends on the computational power. So we have three modes of operating according to those three lines, and starting from the bottom, we start development in a development land, then we promote it to testbed and then to operations, and we recently increased our computational power with a substantial contribution of the Japanese government, and we roughly have 20 times more of computational power in the operations than we had previously, and that allows us to increase the resolution in space and then the frequency in time of the input and outputs of atmospheric transport modeling simulations. So if we look at this third column, we currently perform those simulations with a model called FlexBird using two providers of meteorological fields. Having increased the computational power, we are able to provide those meteorological fields at higher resolution. So we pass from 1.0 to 0.5 degree and from 3-hour to 1-hour temporal frequency. We have enough computational power to introduce another atmospheric transport model, FlexBird, running also on two sources of meteorological fields. And finally, we will not do it operationally, but only for special event analysis. We'll be able to use the meteorological fields at even higher resolution. So this is the highest resolution provided by the European Centre for Medium-Range Weather Forecast, which is 0.125 degree, and then probably also going towards mesoscale modeling in order to analyze the events of interest. So I'll stop here and thank you for your attention.
So good morning. My name is Pierre Mial. I'm the acoustic officer for the International Data Center. And while I will talk about a little bit about the infrasound technology, I wanted to emphasize something that has been of a major interest for us and for the scientific community that was working on infrasound this year, which is this large explosion over Russia in February 2013. And why I will explain a little bit why it is important for us as well. And since we were here at the AGU, I thought it was interesting to talk about something that is of interest to the scientific community. But before I go into the detail of the meteorite, just to let you know about the history of the infrasound network, the infrasound technology has been renewed thanks to the CTBTO. So this network that we are operating in Vienna is quite new. And here you have a picture of the global network, and with on the right a few installations of stations in very different environments. And what is interesting is that basically 12 years ago we had only one station that was certified with high accuracy, and now today we have nearly 47 stations will be certified at the end of the year. So it allows us to start to do global studies, and this is one of the reasons why we've been looking at the meteorite, because we have this large network that is kind of unique, and that's been used by us or by the scientific community to analyze the Russian fireball. So this fireball, it's very unique for us. It's because it's the largest event that has been recorded by the IMS Infrasound stations. So it has produced a signal observed at very extreme ranges. And it's also the most energetic event detected by the network. And after studying with my scientific colleague, they concluded that it's something that will occur only every 50 to 100 years. So it's something of great interest for the infrasound community. And what is interesting for us, CTBTO, is that it allows us to study in detail the infrasound propagation around the globe, which is not so obvious. And it allows us to calibrate the performance of the IMS network. That's what we want to do, because we want to be sure that we are monitoring globally when we are looking for nuclear explosions. So that's provide a good benchmark for further studies on exploding fireballs, as well as atmospheric sources. And it helps us to advance the development of monitoring procedures at the CTBTO on outside, in particular to identify dangerous near-Earth objects. So here, what I want to add is that this is something that we have been looking at, this specific event, but it's also something that we've been looking at with the scientific community. There's a lot of people out there that have been looking at it, and there was this session on Tuesday on the meteorites, and there were many presentations using or not using infrasound data. So this is something of great interest, and that will be for the years to come. And why is it of great interest? Because it's the first time we had 20 stations of the 42 that were operational at the time that detected it. And in particular, here on this map, you have the red start as the station that detected the signal from the meteorite, so with infrasound content. And this is, you can see that it has been detected globally. The station that didn't detect it were either noisy, not operating well, or for specific propagation pattern did not record anything. But basically, half of the network recorded it. And what is very interesting is that we have, out of these 20 observing stations, we have even multipass. We have multiple detections at some of the stations. So here it's an animation on the right that has been where I sped up the time of the recording to make it audible. So I guess we don't have sound, but if you go on the ctbto.org page, you can hear how this explosion would sound like in Kazakhstan. And on the left side, you have basically all the trace for all the stations that regarding it, with the colored box that are for all the detections. So some of the detections, some of the stations that recorded twice the energy of the balai passing by, either because of the direct path from between the source on the station, or either because the propagation was reversed around the globe. And even more interestingly, at some of the stations, very few, like for instance Alaska and Fairbanks, the acoustic wave were recorded not only once after the first propagation toward the station, but also after a full circumnavigation around the globe, so almost 2 days later, and again after a second circumnavigation around the globe, almost more than 3 days after the event occurred, we could still register energy coming from the meteorite. So basically, this explosion generated acoustic energy and acoustic gravity energy that was everywhere in the upper atmosphere, and that was recorded at very extreme ranges by our sensors, and which is of great interest for the infrasound community, since we are interested in this, until which extent we can really use our sensors and our capabilities. So, as I was saying in introduction, this is of interest because of extreme ranges, because it's a very large sources, the most energetic since the Tunguska meteor that was recorded in 1908, and because it's something that is occurring only every 100 years. So if you want to know more, there's a few papers that have been already published in geophysical research letters or in Nature last month, which show you what the scientific community has been doing with these sensors. And the last message that I want to give you is that not only we are monitoring meteorites, and of course we are looking for nuclear explosions that don't occur in the atmosphere since the CTBTO has been started to work in the end of the 90s. But we are also looking at other sources since we want to test our sensors and we want to advance the infrasound knowledge. And in particular, we are looking at major volcanic eruptions, since it's of interest as well to some centers like the Volcanic Ash Advisory Centers working with the ICAO. And we are working on the global remote monitoring volcanic activity with some outside colleagues. And also we are working with the scientific community to advance the knowledge of the upper atmosphere, so to study the atmospheric dynamic. So this is not something that we are doing ourselves, but something that we are doing with the scientific community. And there's many of these scientific civil applications that are possible with the IMS network, and I think it's something that Monica will be presenting tomorrow in the CTBTO session. So if you're interested, please come and pass by the CTBT session tomorrow. Thank you for your attention.
Okay, do we have questions?
That was a very interesting discussion. Randy Shostak, I'm a reporter with EOS, newspaper of the American Geophysical Union. I'm wondering if you can tell me what, if any, role does or will the CTBTO have related to the current negotiations regarding reducing sanctions in Iran? And is the IFE-14, which will be located in Jordan, related to that?
Well, our role is to monitor for nuclear explosions, and as Under Secretary of State Rose Gottmuller said on Monday, so we are putting roadblocks on the road to any nuclear arms race. So we are part of a global regime, and that is supporting a non-proliferation and disarmament effort. But again, our mission is to verify for compliance of the treaty, and I will let Gordon respond on the role of the IFE-14 experiment.
Okay. So one of the things with the IFE-14, the state parties were the ones that selected the location of it. So you can read what you want as to why it was in the Middle East. It was the selection of that. There's a number of things that are going on there, nuclear-free zones and other things that state parties may be wanting to look at. But Iran is a signatory to the CTBTO, and so they are actually part of the verification regime as well and actively participating in it. So it's not it and the IAEA piece under the NPT are slightly at different levels, as Patrick was just saying. So it's I think there's an interest in the Middle East, and that's one of the reasons the IFE-14 is located there, but at the same time it's not necessarily directed at the Iranian issue.
Steve Benko with Physics Today magazine. One of the stumbling blocks, shall I say, to ratification, at least in the U.S., seems to be a concern about detecting clandestine activities. Now, I know there are other technologies in the monitoring system, like seismographs and such. Can you talk about detecting sites that you're not aware of? Obviously, you can't do an on-site inspection if you don't know that the site is there. Noble gases may or may not escape from an underground cavity. And you know, the whole issue of decoupling a small explosion from the surrounding earth within the cavity might render it invisible to seismographs. Could you address some of that?
What I would like to refer to is the study that was carried out by the U.S. National Academy of Science and that published the results in 2012, and that really looked into those issues. Of course, we are not weapons and experts in the CTBTO, and our role is to detect for any potential signature. But what we see is that with the current performance of the network and the fact that we are still building and improving performance, we are capable of detecting any nuclear test of relevance to potential military application. Again, this is not coming from us, this is coming from the report of the National Academy of Science.
And this is Gordon McLeod. I just wanted to add on to that. One of the things that once you have entry into force, then you do have on-site inspection. And yes, while cavities, for the most part, will can contain the noble gases and things like that, our studies, this goes back to 1993 when the U.S. did the non-proliferation experiment in Rainier Mesa, shows that the gas will actually percolate out. And so eventually you will have those gases will come to the surface, and in an on-site inspection we actually have a technique that we are using to actually pull soil gases out and then run those through both argon and xenon noble gas detection systems. So you know, you have the possibility, once you have entry into force, of being able to put the people on the ground, and the actual triggering event or measurement for causing the on-site inspection is not based just on IMS, it also is based on national technical means. So it's a much broader group of detections that can be used.
Megan Seaver, Earth Magazine. I was wondering if you could address sort of how fast the mobilization is. So when you detect something, you know, in the atmosphere, when you detect the infrasound, of how fast do you guys react to that? How fast are you then, you know, sending someone to inspect on the ground?
So I can answer for at least for the detection part. So for seismic, it's very fast. It's within a few seconds. The automatic system will pick it up, a few seconds to a few minutes. For infrasound, since we have the infrasound propagation, which is quite slower than the seismic waves, it will take more time. Basically, 1,000 kilometer propagation takes 1 hour to be picked up by a station. So in the case of the meteorite, it was 600 kilometers away from the station in Kazakhstan. So half an hour later, the signal were recorded in the station. Then we received data within a few minutes in Vienna, and automatically it was processed. So basically within an hour, we still started to have an event built automatically that we could look at. And I remember that in this morning we had a briefing for a different topic, and I was receiving some alerts on my computer saying that there were some very large waves coming to in Kazakhstan and Russia, and then by the end of the day there were more and more stations that were starting to record it. So that's why this takes some time, but we are building it automatically, and then we are just refining the location and detection as the information is coming to Vienna. So at least that's for the detecting part.
And you basically tripped into a political part. So once you have entry into force, the IDC will provide that information to the state parties. They're going to have to make a decision on whether they need to have an on-site inspection or not. And so then that becomes a political process. The on-site inspection trigger is when the request goes from that state party, and we have 6 days from that request to be in country. Starting the inspection. So there's a very short time frame once that trigger goes in. There's actually a political decision that has to be made within 96 hours of the request as to whether the request is valid or not, and whether they're going to go forward with the inspection. So it's a very quick trigger when you talk about 100 tons of equipment.
Is there anyone on the phone with a question?
Hi, Randy Shostak again with EOS. I wanted to follow up on an earlier question and ask, is there any way for countries to effectively mask testing? And Related to that, what do you see as the greatest weaknesses and needs of your system?
I will probably start with the weakness of the system is really the entry into force, as Gordon mentioned, because once the treaty has entered into force, we can deploy a full-fledged on-site inspection. That is a challenge inspection in the country, and with all the techniques that he presented, that's really a way for us and to go very, very far and in a very intrusive way into what a country or potential violator of the treaty could have done. So for me, this is the main weaknesses so far. Is entry into force, and as indicated earlier, and even with and very low yield test, and as was the case in 2006 in DPRK, we managed to demonstrate the ability of the system to detect. And by the way, we had a very interesting situation in February this year because we registered the seismic and infrasound waves from the DPRK event just after the test, as Pierrick mentioned. But 54 days after the test, we had a sniff of xenon gas that was detected at one of our radionuclide station in Takasaki in Japan. So most of the people thought that after 2 or 3 weeks after a potential event, it would be difficult to detect xenon. And suddenly 54 days later, we managed to detect 2 isotopes of xenon at that station in Japan, and backtrack through atmospheric transport modeling and to the Korean peninsula, and showing full consistent with an explosion that would have taken that would have been done in 54 days earlier. So it really shows the potential of the system, even when most of the people would not expect the system to detect.
Well, I just wanted to follow up then with quickly. So would you say that there's great confidence that there is no way that that a rogue nation or a rogue party might be able to effectively mask a test?
Again, it's a matter of magnitude produced, and there are some facts that the system has a detection threshold that keeps becoming lower and lower with time. So we keep improving that. But and again, I'm referring to the National Academy of Science study that had a very interesting perspective of showing the perspective of a potential violator of the treaty, and looking at the percentage of chances and a potential violator would get to be successful in masking a nuclear explosion. So you have a number of conditions that need to be to happen exactly at the same time, and lowering the probability to a very low level. But again, I refer to you to that study that shows that the probability is extremely low.
The other thing I might reference you to is actually Terry Wallace's talk that he gave on Monday. It has some really good graphics showing what the probabilities are of detection, or the probabilities of being detected, depending on how you look at it. And so, and the system is much lower in the detection threshold than what was originally laid out when the network was actually envisioned before the signatory and the signatures on the treaty.
Any other questions? Questions from the chat? Okay, well, thank you very much, panelists, for your presentations, and thanks everyone for participating. Our next press conference will be at 11:30. Titan, as you've never seen it before, new results from the Cassini mission to Saturn.